There we go. Okay, we're online. Okay, so let me reshare again. That's a tautology. I'm sorry. Share screen, not screen, MATLAB. Okay, you should just see the MATLAB now, not anything that's covering it up. Where was I? So, let's do this. There we go. In the chat. Okay, Nikolai's just typing. So I'll scroll down and show you guys the fill slice. Recognize this recording doesn't include the first part of the Sudoku solver discussion, but you can kind of see the code when I was showing it earlier. And I'll post the screenshot with with the YouTube video once I upload it to the unlisted channel. So yeah, I'll make that available to you. It won't be in the actual recording. So the fill slice, what that does is, I kind of talked about it earlier with what it does is a few things. So first of all, it has to check whether the sum of the slice equals 0. What this does is just the number of empty. I mean, it's called n-empty. If it's equal to 1, if 1 empty, then fill the slice. If not 1 empty, then do absolutely nothing. Because if it's more than 1, which number goes where? And if it's 0, then let me put it down here actually. If it's 0, then already done. That's the rationale behind that. And this one down here just means if it searches the box or the box, a row, or column, and it makes that part, the empty space, equal to the missing number. That's all that does. And there's multiple ways of doing this. I've seen people talking about so you can sum up all the numbers from 1 to 9, and then you can do that and then subtract from that the sum of the numbers that are already in it. So what another way to do this is, you'll take the sum of 1 to 9, and then you'll subtract from it the sum of slice. That's another way you can do it. And then that's going to be your missing number. That's another way you can do it. That's about it for the fill slice. I mean, what it does is pretty straightforward. It's a little bit convoluted in some of the coding, but it's it works. Okay. Still recording. So I'll give you guys a few seconds to take a screenshot as well. Five, 4, 3, 2, 1. I'll clear this. All right. Any questions so far in the Sudoku solver?
In the document, they said to make sure that it doesn't loop. It doesn't loop infinitely. Otherwise, we'll fail it. So if it happens that it can't solve it, what should we output?
If it can't, I think the understanding is the Sudoku input, the grid that you feed it, should be solvable. You shouldn't have anything like, here's an example of something your thing to solve. Let's say this is a top left box, here's the rest of the grid, and then you have a 0, 0, 0, 0. your code may not be able to solve that. Like this special, but this is a special case. So, but you may be able to solve something like if you have 0, 0, 0, 0. Your row and column won't be able to handle that, but since each of them is in their own grid, then it'll be fine. But yeah, if you pick, the key is picking a small enough empty spaces. Like you'll notice I did like 15. Let me see if I can. Grid equals, yeah, 15 empty spaces. And this is just a seed. I mean, change this number to change the Sudoku puzzle. But unless you get really unlucky, I guess. I'm sure they configure the test cases so that it'll work with a simple case. But just pick a small number of n empty. Use like 15 like I did. Let me see what the PDF says. I believe they kind of recommend a number for n empty. Let me see.
When I tried seed of 3, I had a lot of issues with it at first until I altered my code to make sure that if it was too difficult to solve, that it came out with something saying that.
So it worked out?
Like I had to come up with an error saying like this puzzle was too difficult to solve. Like if I put in 3, if I put in 3 for the seed and then like.
I'm curious if that's the case for this one.
Okay.
Grid columns. Okay, well that's the make Sudoku one. So let me see. Let me just run the Sudoku solver and see if that actually loops. Grid out equals. So why is that unsolvable? So that's zeros. I see, yeah. Some of these will be. So, okay, what's interesting is this doesn't include an infinite loop, I guess. Oh, I see. I think the reason this doesn't infinitely loop is at the final pass of while, the final while pass, there is it scans over the rows, scans over the columns, and scans over the boxes, and nothing changes. The elegant thing about the way they set up this while loop, now that I'm thinking about it, is that it stops the code either if you're done or if you run over an entire pass and nothing changes, which means like you can't do anything more with it. So yeah, you shouldn't have an error code in this. You should have a thing that checks whether like you have like no more moves, like a no more moves case, where your code just can't solve anything more. That's what this does. So like study this part of the code, like where it says like while any grid out is not equal to grid.
I guess what I'm saying, I put in a while loop. It's not exactly that one, but it's similar to that one. But I basically said that if that happens, to say like provided Sudoku grid is too difficult for the simple solver. Is that not what they want? Based on
this the solution formatting, I think what the proper format, the proper solution, the proper output, I should say, that you want to have for grid out is just if that happens, then you just output grid out. Okay. Then just output the one that I can't solve this anymore, but this is the work I have, that kind of thing.
Okay, thanks.
Okay, I've seen some stuff in chat. Let me read that. Oh boy, let's see. I'll start from the bottom and I'll go up actually, just so that I'm not missing anything. Num E1 in the code. This is the number of elements in slice. Okay, yeah, Nikolai. So this should always be 9, I think. 9 in a row, 9 in a column, 9 in a box. Maybe this changes if we decide for like a 10 by 10 Sudoku or whatever. We can use length naturally, no, we can't, because in case we have a box, right? If you take the length of, so there's a function you can use called like, let's just use like 1s 3, comma 3. The length of this is 3, which is, it's not 9. So we need to use the number of elements, num l, 1s 3 by 3, in order to handle both vectors like rows and columns and like 3 by 3s like this one. That's the reason. Let's see. Yeah, Nikolai answered that. Make Sudoku.
Hey, what
Wait,
is the 4 in the sub? The little break at the bottom.
Oh, this one? It's just if any of them is, if you find the empty space, fill it in and then stop looping. Break this whole loop. Hold it. Are you guys given make Sudoku? Is this not something you're given? I'm seeing some people like, it should be in the
It's
download
given
folder.
in the files.
Okay, yeah. For people who can't find it, it should be under like the same place you get the lab4 files. It's just like a function like this one. Let me know if you can't find that. To some functions. Yep, Nikolai's been answering. Thanks, Nikolai. Big help. Okay. Does anyone have any further questions on this? Going once, going twice. If not, I'll move on to the next one. I'll give you a few seconds.
Yeah, I had sort of one question.
Yeah.
So is like our code not like allowed to like, since you guys showed us it, is it not to like allowed to like resemble like any part of this code, or can it? Like, can we incorporate like a certain part or not?
That's a good question. Code it. I would try coding it yourself, just so that you have the understanding. But some of these is like, for some of these codes, there are just not too many creative ways to changing it so it's like your own thing. Maybe the ordering of certain things is different. Maybe the syntax is different. But overall, like the way we grade these is like because here's the thing: the professor knows that we're showing, like he advised us to show solutions in lab, so he knows that this is you'll probably have something so closely resembling this, but code it for your own benefit. That's kind of the stance we're taking. Do it yourself and then use this as an answer key, that kind of thing. But if you're stuck, I mean, we're giving you the solutions. So this is a resource we're providing you. So feel free to use it.
Okay, thanks.
Someone asked me to demonstrate make Sudoku. It says Sudoku. Not this one. Nope. Sure. Okay. Seed, number of elements. Seed of 3, 15 empty elements. And there. And this is what the grid should look like.
Wait, so we should have make Sudoku like downloaded for my Sudoku solver to run?
The lab one, the lab tester, yeah, the lab 4 tester, it should have already have a test case. So if you want to just run the tester and not bother with making, go ahead. If you want additional test cases, this is a way to make them. It's also handy if you just want to like make Sudoku puzzles for your own, pleasure. I'm not sure if you're into that kind of stuff, but. Unrecognized. Search path. Look your current folder and see if right over here, and make sure that your make Sudoku or whatever function is in that one. So you'll need to do a little bit of management inside your file explorer or finder, whatever you use, and make sure that what the function you want to call is in that current folder. That's a common question, by the way. So make sure you I think it produces a lot of errors that it seems like your code's right, but if MATLAB just doesn't see it, then you're like, wait, where in the code is my code wrong? But it's not your code. It's just where do you place the files in your file explorer. So long as it's on the search path, it's fine. So long as it's in your current folder. Okay, did I miss anyone? Nikolai answered that. Let's take 5 seconds to kind of browse through the chat. And yep. Shall I move on to Monty Hall? Okay. Let me clear the drawings. And we'll move on to a brand new car, or a goat, depending on what you choose. My Monty Hall. I forget if this is actually called new car or Monty Hall. Doesn't matter. Code it according to what is in the audio grader. And spell it correctly. Make sure that, like, this is... Sometimes this is a spelling class. Like, there's sometimes where, like, the mistake in your code will just be a single letter. Think that for the, what's it called? The my greeting function from, like, lab 3, I think I don't know how many people, but, like, people in lab are asking me about, like, oh, what's the error in this? It's like, add a period. Like, part of that is, like, just because you're given this entirely long string, and then you're expected to spell the entire thing correctly. If there's one error, then it marks it wrong. But, yeah, that's kind of like a common annoyance, so don't feel bad about that. Where are we? Monty Hall. So this explanation is going to assume you have a kind of a general understanding of the problem, but there's a lot of videos and articles about it. It's very famous, very interesting actually. It's a paradox, but like not an actual paradox. It's just unintuitive. So let's see what this is trying to do. Format short. This is just for display purposes. I think it's just for displaying your win rate as like 0.33 versus like 0.336, blah, 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 blah. So here's what we're going to do. Here's the initialization. Win counter equals 0. And this for loop right here is going to run a bunch of simulations. 1 to n simulations. So n is going to be the number of sims. Give me 1 second. Let me move this. Oh, I wasn't hiding. It's too much. Number of simulations, your guess, which door you guess, number door, you initially pick, that is. You can stick or switch, or in this case, stay or change. And based on that, you can stick to the original door, or you can switch to the other one. So let's say this is 100. 1 to 100. We'll have, to randomize the car's position, we'll have 3 doors, 1, 2, and 3. Let's say we pick 1. This is our guess. And then the car is going to be behind 1, 2, or 3. One of these two. Here are the 2 conditions in which we win the car. And the idea behind this problem is we kind of want to see which wins more. Because each of the stay and change, each of those methods is going to correspond to one of those win conditions. Let's do win number 1, win number 2. Win number 1. We, first of all, stay with our original choice, right? We guess 1, and we win if the car is behind door number 1. This is win condition 1. So when Monty reveals a goat, and we don't want to switch to the other one because this is also going to be a goat. And the car is going to be here. So that's win condition 1. So stay and car equals guess. It's reversed in the syntax, but it doesn't matter. Then And to track that as a win, we do win counter equals win counter plus 1. So win counter plus 1, that's 0 plus 1, and then our first win counter is 1. So we have our first win. Second win condition, we pick the wrong door. Let's say the car is not here. It's behind door number 3, all the way over here. In this case, we're going to change, and because Monty's always going to reveal a door with a goat behind it, that means that if we switch, we are guaranteed, if we didn't pick the car first, to win the car upon the switch. So this is going to have a goat, this is going to have a car. So this second win condition is change, and we did not pick the right one on the first go around. Car does not equal guess. And this one just down here, this is just collection. Win rate is equal to the number of times we won and the number of simulations we had. Let's say 100. You'll notice that there's no like else statement here. That's perfectly fine. Not all if-else trees need an else. If we did put an else though, all other cases we lose, right? The reason we don't need to have an else case is that's just win counter. I'll abbreviate it as win C. Win C equals win C, because we don't do anything to their win counter because we didn't win. If we lose, nothing happens to our win counter. We don't add anything to it. It's like win condition plus 0. But because this doesn't do anything, we might as well just not include this line. We don't need it. So that's why there's no else. And that's about it for my new car. And I'll open this up to questions. Let me check chat as I'm doing this. How do people generally feel about this problem? Re-explain the if-else if. The if-else if are the two cases in which we win because of this collection thing on the bottom, the win rate equals this one down here. What this does is it collects wins. And we'll want to have an if-else if for each win condition. So let's go through the logic line by line. 1 to 100. So we'll run 100 simulations. For each simulation, we'll have a randomized position of car. We'll go down here, and then we'll randomize, oh, is car here, is car here, is car here. Now, once we do that, we're going to go into this first if statement. Let's do an example. Let's say car's behind door number 3. Here's door number 3. I'll do 1, 2, and 3. If we choose stay, okay, let's say we choose change. We want to do change. Well, look at the string comparison between method and stay. Do we stay? We picked change, so this is not true. So we only need to check this part. But if we did, guess equals car, that's not true. So we wouldn't win anyway. Now we go to the else if. String comparison between change and change. Yep, that's true. So we picked change as our method, and our guess is not equal to the car. Well, we guessed 1, and the car is behind 3. So if we change, we are guaranteed to get the car, given that we didn't pick the correct one on the first try. So we go into that, and we say, yes, we win the car. Win counter equals win counter plus 1. And we'll do that multiple times, and each time the car is going to be like here, 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 here. It's going to change every single time. Let me know if that doesn't answer your question. I can go over the more detail somehow. Okay. 15 seconds to screenshot this, and we can move on to the my majority. Y'all any more questions or type them in chat? 5, 4, 3, 2, and oh, see a question? Oh, that's just Nikolai. All right, clearing all drawings. Now, where was that majority function? Found it. My majority, question number 3. How do people feel about this problem? I'm just curious. Was it okay? Thumbs up, thumbs down?
Not too bad. I'll talk about this problem in the way I would tackle it, because there's multiple ways of handling this part of the code, right? For the J, like especially this part. I'll expand this out and I'll kind of create some more empty space over here. There we go. I'm gonna clear this. Here's what we're doing for this. If we have an array 1, 1, 1, 2, 4, this is a majority. Majority equals 1. 1, 1, 2, 4, this is not a majority. So therefore, M equals nan. All right, so how do we want to do this? So here's just some initialization up here. We'll need this later on in the code. A lot of these for loops have you initialize something and then for, and then loop over that. But we need to initialize this first, this majority equals not a number, because it's our default, if we don't have a majority, we return not a number. So, but we loop through the for loop, and then if there's a majority, then we'll replace that not a number. But if we don't do that, we just leave it as not a number. What is this for loop trying to do? So there's a couple things there's a couple for loops here, but the way I'm going to teach you is you don't need this for loop right here if you don't want to do it this way. So the idea here is we're going to take, let's use this one here as another example. Let's look at just one. I'm looking up here, this for loop right here. I equals 1, ... and array. So this is going to be like 1 to 5. The first index, I'm going to look at this and I'm going to say, is this the majority? But so how do I code this though? What I'm going to need to do is generate an array of booleans. I'm going to take this out. I'm going to say 1 equals I'm going to say my array. Now my array is going to be this one over here, so I'm going to compare it, and I'm going to get trues and falses. 1 is equal to 1, that's true, so I put 1. 1 is equal to 1, that's also true. 1 is equal to 1, 1. 2 is equal to 1, well that's not true, that's 0. Same for 4. 1, 1, 1, 0, 0. Here's how we tell whether this is a majority. It's this, where do I find it? It's this one over here. By the way, what I just did here is this majority, this part. All of this is just this for loop. I don't need to loop over all of this because, I mean, what they kind of did is like they did this Boolean array. They constructed it element by element, but you don't need to do that. You just do it in one fell swoop like this one. Okay, is this a majority? We're going to sum up all the trues like this, the number of truths, which is basically saying the sum of this array right here. I'm going to call this like bool array, but they called it n here. So sum of the Boolean array, that's this one over here, is that greater than the number of elements, the length of the array divided by 2. In this case, it's 5, right? So you'll get 2.5. So is it at least 3? Here it's at least 3. So you'll get 1 plus 1 plus 1. So this is 3 greater than 2.5. Okay, solid. Therefore, majority is equal to whatever number we just found. Now be careful. So we'll need this break right here. This is a very important piece of code. Because what happens if we don't have this? Well, we're going to end this. We're going to go end, and we're going to go back to the for loop and repeat this entire process. And we're going to go 1, 1, 2, 4. And then the last call to the loop is going to be 4. And I mean, okay, I guess we can do without this break, but it'll take longer. Because we're not going to, because if it's 4, right, this isn't going to do anything. This if statement isn't going to run because it's not a majority. So I'm pretty sure you don't need this break here, but it makes the code run faster because you don't need to calculate anything more once you found your majority. You found your majority. There's not going to be 2 majorities the way we constructed it. It's not possible. So once we have this majority, we'll return that and output it up here. We'll break this loop, and then we'll have a value for majority that's not a number. All right. Open this up for questions then. Is there anything I didn't clear up? So that's about all the solutions I can show. I can go back to like the Make Sudoku, My New Car as needed. So here's the breakdown of what I covered and then what the professor covered. So let's use a different color. So here is to orange. So today I covered 3, 4, and 6. See the professor's lecture recorded for 2 and 5. So this covers about 5, 6 of the questions. So use the lecture for 2 to 5, use this for 3, 4, and 6. So if you're looking to reference one particular problem. And we can go over 1 if you want, but I feel that's, compared to the other ones, pretty straightforward. It's just, there's a little bit of trickiness, but not too much. Okay. I don't see any questions in chat, but I'll stay on for another hour, and then just Q&A, ask any questions you may have. It can be on the lab, quizzes, anything. And by the way, there was a question on the quiz, quiz 11, and I believe question 4 was incorrect the last I saw it. It's just, I asked on Piazza, just the instructors, to fix that. I need to check whether they actually did that or not, but like that should be fixed. So we'll take care of that. Okay, I'm gonna clear this in like 10 seconds or so.
Dennis, I have a question.
Sure.
It's only like about like a very specific line on like my Sudoku. I mean, you said to look at it, but like I've been looking at it and I'm still a little confused on how it works.
Sure.
It's like
the while.
Oh, yeah.
Yeah.
Like I'm trying to read how it's functioning, but then like I'm like it's just returning a bunch of 1s, but then it's checking if any of those ones, if there's a 0 among those ones, or
Okay, yeah, yeah. Let me clear this drawings first of 5, 4, 3, 2, 1. Blast off. Let's go back to my Sudoku. No, my Sudoku solver. Whenever there's a piece of code like this, I always like to just plug something in. Let's do this very simple case. 2x2 matrix. We're doing a 2x2 Sudoku puzzle. A baby could do this. Grid out. Let's go through the logic. Grid out equals a bunch of negative ones. Our grid's going to be something like, let's say 1, 0, 2, 3. No, wait, that doesn't make sense. 1, 2, 0, 1, 0, 2, 1, because there's only 1 and 2. While any grid out is not equal to grid, there's a couple things going on here. Any, why do we need any? So if there's any ones, right, this right here is, you'll see this a lot in this lab, it's a Boolean array. So GO not equal GRID. This is a Boolean array, an array of Booleans. That's not how you spell Booleans. Boolean array. And what it's going to look like is, let's say we just do a first pass on this. Grid out, none of these are equal to grid. So therefore, it's going to do 0, 0. Oh, no, wait. This is not equal to. So therefore, we need to do this. Not equal. So all of these are actually going to be ones. Come on, eraser. And I was talking earlier about this is how, like, kind of like a key to the while loop. This is always going to be true. There's never going to be any negative ones in the grid. So this is our Boolean. Why do we need 2 any's? Well, because one any does this. Any equals 1, 1. It just sums up over, it scans over each column and says, in that column, are there any ones? Yes, there are ones. Yes, there are trues. So therefore, this entire column is true. Now, we need to run another one, any, this, to say, hey, are there any trues in this? There are. So what any does is any number in this Boolean array true? That is any, if we kind of zoom out a little bit, is any number in grid out not the same as grid? This will make more sense once we do another pass through it. And then let's say, oh, we plug this in. Oh, we'll plug 1, 2, 2, 1. This is our, no wait, this is still grid out. This is our new grid, 1, 2, 2, 1. Are any of these elements not the same? Well, this is not the same, the 0 and the 2. So we'll just do another pass through it until this becomes 1, 2, 2, 1. And then we'll just output grid out once all of these are matched up. Now, there was a case earlier where, like, you still have some zeros in grid out. But here's the elegant part of this, right? This is our initial grid out, right? We've assigned grid out over here as 1, 0, 2, 1. If we do another pass through it and we still don't fill anything out, we scan the rows, we just did everything, but we couldn't fill in any zeros, then we're actually also done. We don't need to finish this puzzle to output grid out. We just need to reach a point where we can't make any more moves. Either we solve the puzzle or we can't solve the puzzle anymore. Either one of those cases. That's what this does in a nutshell.
Okay, yeah, that makes a lot more sense.
If you're ever confused about something, just plug in numbers. That's how you find patterns. Simplify. Let me check the chat to see if Saloni, wait, is Saloni still here? Oh yeah. Let's see. It looks like Nikolai is. Saloni, did you want to go to the breakout room or the main room? Up to you.
I did question 3 slightly differently, and I'm not sure it works. Like according to the lab test, it worked. But like I wanted to just show my code to you.
Sure. Privately or publicly? Yeah.
I'm
If
okay with showing it here.
okay. Let me just stop sharing then. 5, 4, 3, 2, 1. All right. Go ahead.
Yeah, just a second. Yeah. So can you see it?
I can. Yeah.
Yeah. All right. So I did this, and it looked really simple, and it works according to the lab tester. But after looking at your code, I'm not sure, like if I've done something wrong.
For example, like the n arrays kind of thing.
Yeah.
Yeah, the n array is not necessary. What you're doing for like I equals my array, that works. You're just taking an element. You're taking. Let's say we have the. I can still annotate. We have the 1, 1, 2, 1, 1, 1, 2, 4. And then we're just saying, oh, I is 1, 1, 1, 2, 4. That
Yeah.
works. And Boolean array equals my array equals. Yeah, so you're pulling out 1, you're making a Boolean array of like, I'll do like just the ditto mark. Equals equals I. Now let's just properly write this out. Equals equals 1. That's going to be a Boolean array. And then if the sum of that Boolean array is greater than. Okay, the default for this problem is not no majority. It's just not a number.
Oh, all right. Okay.
You also want to. I think you want to place that above the for loop though, because let's say we run this thing and majority is 1. Great, but we'll keep looping and we'll do 1, 1, 2, 4, and then the last for loop is going to do this 4, and it's not going to go here. It's going to go here, and then the final value of majority is going to be no majority.
All right. Okay. Yeah.
Either
Okay,
break,
yeah.
either put a break here, or just scrap this and put a majority equals nan up here. One of those two
All
should
right.
work.
Okay. Okay. So I can put a break there as well, right? Instead of
Yeah.
changing all of it.
Yeah.
All right. Okay. All right. Thanks.
Well, actually, there's one more thing you need to do though. You want to make sure you have some code that says majority equals nan if there's no majority.
All right. Okay. Yeah.
Check the PDF on that. Well, for what they want you to do for that.
Okay. Yeah. All right. Thanks.
Mhm. Okay, people asking for breakout rooms. Would you guys be fine sharing in the main room? If not, that's totally fine.
Yeah, I mean, I'm fine with it. I'm having troubles with my new car one, which initially I had something else, but then I just like wrote down exactly what you had, but like it's still not working through the tester. So I wanted to see like why.
Can I see?
Yeah. One sec. So I believe this is what you had on yours.
Oh, don't do rand 3. Do random integer 3. Rand I.
Oh, okay.
Door 1, door 2, door 3. There's no such thing as a 2.7 door. Door 9 3/4.
Oh, okay. Then
Yeah.
yes, that's the thing I was missing. Thank you.
Yeah. Yod? or do they?
Here,
Oh.
I'll share my screen in just a second.
Okay.
It's weird. I followed away by your syntax for the My Sudoku solver, and I keep getting output argument grid solved, not assigned.
You want your output to be. I mean, you have grid M and grid solved. Which one do you want to use?
Oh, so I would just use grid solved here.
Mm.
Oh, I thought it was a completely different variable. Okay.
Change all of those, by the way.
Yeah, I'll do that real fast.
Interestingly, I've seen a lot of different ways of spelling Sudoku. It's like Sudoku.
I'm not sure. I'm not sure even if it. Wait, let me see the lab tester. Sudoku. Okay, yeah, spelled it right. Same. Let's see what we got. I think
The
that's
fun fact, by the way, like if you actually look at how the this is unrelated to the coding, but like if you look at how it's spelled in Japanese, like the Sudoku, it's actually not Sudoku. It's like Sudoku. It's like there's two U's. It's a long U. Sudoku. This means math. I forget what the doku means, but
Mm-hmm.
let me clear that.
It's actually really cool. I learned how to play Sudoku like 3 months ago. Yeah,
If you
so
now that you have the what's it called, the make Sudoku, you can create as many Sudoku puzzles as you want.
Mm-hmm. Let's see. I'm just gonna check if what you told me earlier works. If I were to use sum instead, we have sum slice, but we have also a sum here. We could say this is the same thing as sum through 1 minus. I want to just have it a little bit different, if that makes sense.
Do your own way. Okay.
Yeah, just to like see every different variance. That looks right. Yeah. So let's see.
That's not a Boolean, by the way. The sum. It's like if you have a number, like you have if number,
Mm-hmm.
you'll need to do like a 1 or a 0, a true or a false. That's the only thing that if statements understand.
Oh, it's not Boolean, huh?
Yeah.
Wait, what was I looking at? I was looking at something else.
What do you want that to be equal to?
Oh, 0?
Let's see. Do we even need an if statement here?
I don't think so. I would say, actually, no, we could just do this, right? We could reincorporate the any's. Then we have this any. Then.
What are we doing with this sum 1 to 9 minus sum blah blah blah? What is that going to give us?
Oh, that's gonna like subtract. That's probably gonna give us the numbers that we need in our Sudoku.
It gives us the exact number that's missing from that row.
Yeah. Exactly.
What do we want to do with that?
We want to input it in here.
I'd say just
Right.
get rid of that if, and then just see that number right there. Just put that into our slice. Look at what that slice equals 0 is. Slice, and the index of that is wherever slice is equal to 0.
Oh, okay. So we're gonna remove this if, and we don't need these any's.
You don't need the if. You don't need the any. Just that sum part.
Okay.
And then you're gonna put that in the slice.
And then we're gonna put this all Command C in here, like that.
No. You keep the left side of that assignment. That's what you want to assign it to. That's slice where there's an empty box, a 0. You want to assign this line you're highlighting to that empty space. Fill in that empty space. Here, that's my hint to you. I'll let you try that in your own time.
Okay, no worries. Yeah, I can figure that out.
Sure.
Thank you.
Dennis, I had a question. So for like I guess the Sudoku problem in general, should we always expect like 1 through 9, or should we make our code so it can like handle different situations? Or
I
like,
think we're sticking with the 9x9 on this one. Because
okay, cool.
if I'm thinking about it, if we make it a 10x10, we're gonna need to modify the boxes. Like I'm not sure what it's gonna look like. But yeah, 9x9s.
Thanks.
If you all don't have questions and like don't want to listen to anything else, you're free to go if you already like stayed the 2 hours. Just a reminder. Simply stay if you want to ask. Like this part's just office hours. We're done showing solutions for the day. But yeah, don't let me waste your time. Okay, concept of question. Which question? Question 1. Let's just do a whiteboard for this one then. So the question was privately sent to me regarding question 1 and what that, like the idea of that. Fn is equal to, so here's like the basic Fibonacci sequence. Fn equals Fn minus 1, Fn minus 2. 13 equals 8 plus 5. Or 8 equals 5 plus 3. Now, we can modify this and be like, oh, this is actually A plus B. So the concept of this is that there's this general case where we have the function, right? This is our my general recursion. And we want to call this additionally with new inputs. So this is MGR, but with n minus 1. MGR n minus 2. So that's the general case. But there's, all right, general case. But there's 2 like special cases where we don't want to call this thing again. And that's when we get close to the bottom of the sequence. So let's say our F is 2. That's the very first one the very first one that we call. Okay. We have A. Well, how do we define this? Well, it's AF1 plus BF0. Well, we already know what these are. It's x1 and this is x0. So we don't want to call recursion in in that case, because if we plug in 1 for this one, we're going to get like f of 1. This is just like f of 0 plus f of negative 1, and this doesn't exist. So we can't do this. So we'll need to code a special case just for this f2 because we're not calling recursion, we're just calling these base cases. f3, and it's going to be something similar. Now, this will be x1 still, but this one's going to be f2. And we can call this is okay because, well, we just did it up here. And also it's the number we plug in is at least 2. 2 or more is always fine. Integers that are 2, 3, 4, 5, 6. So this is the n equals 2 case. This is the n equals 3 case. All right. I'll stop sharing in 5, 4, 3, 2, 1. Okay, once again, if you already stayed 2 hours, have no other questions, feel free to leave. Question 4, yeah. Quiz 11, question 4. I'll just check that right now to see if they say anything to me back on Piazza. Huh. Okay, they posted something. Let me just read it. Yeah, I'd say hold off on that, but huh. There seems to be a debate on like what the correct answer for that is, but I'm fairly certain. Yeah, I need to think about this. Yeah, but yeah. For now, I think hold off on that question. I'll take a look at that right now, actually.
If anyone wants to go to a breakout room, you can say so in the chat.
Nikolai, actually, a question for you. There was. Have you heard about the quiz 11 question 4? Seems like there was a.
Yeah, is this the linear time sorting?
It's. So here's the thing. If you have a linear versus log, isn't the log better?
Well, if it's just log n, then yeah. But there are no log n time sorting algorithms. So the comparison-based sorting algorithms, which are the most common and frequently used ones, are all n log n. And you can mathematically prove that all comparison-based algorithms are n log n. But there's there's a radix sort, counting sort, and bucket sort, which are sorting in linear time, but they require some special assumptions about the input sequence. I kind of forgot what the specifics of those sorts were, but they were kind of, some of them were taking advantage of the binary representation of the numbers and stuff like that.
So the question was like the best possible time complexity in array sorting algorithm. So the reason why that's n log n is because is it so log n's not possible?
Yeah, so isn't the answer big O of n?
It's not.
No?
There's a
Let's see.
no.
How do you check the answers?
Well, Professor Lee actually messaged me on Piazza with the correct answer. It's not ON.
Oh, okay. Well, yeah, so basically all the algorithms he showed, I think, are n log n, and that's the best you can do for sorting algorithms that are usually used in practice.
Yeah.
Like the more naive ones, like bubble sort, are n squared. Yeah, but the nicer ones are all n log n, like quicksort. And actually, quicksort has a worse time, big worse time n squared. But merge sort, insertion sort are all n log n.
Let's see.
And yeah, so I guess so this is an incorrect problem, since when I look up the answers, I get big O of n as the correct answer.
Okay, that's different from what the professor says. So because there's a better one than n. N log n is better, right? Because you have a linear times like this, so it kind of like bends it downward a little bit.
So the best possible means the lowest one. So the smaller the time complexity, the better the algorithm. So we don't want algorithms that are exponential or n squared, or for example, n log n is better than n squared, and n is better than both n log n and n squared. And log n is better than n. So it's basically the speed at which the function grows.
Oh yeah. And wait, yeah,
so
it goes.
Yeah,
sorry, go ahead.
They should be log n, n, and n log n in that order of increasing.
It's like this. I think this is right.
No, so n log n, n log n grows faster than n because log n is bigger than 1.
How do you draw this?
N log n is.
Is it like this? Oh, no, it's like this, right? This is log n.
Yeah, I think it should be convex. Let me look. Or maybe it's concave.
Yeah. Okay. Let's. Here's what I like to do this. 1, 2, 3, 4, 5. Log of 1, log 2, log 3. I didn't plan this. 1, log 1, 1, 2, 3, log 2, log 3. So 1 log 1, 2 log 2, 3 log 3. So yeah, this is this is biggest. I'll write like number 1. This is number 2 and number 3. Okay, so the reason why it's n log n is because you can't do any better, I think. Like these two are definitely better. But for array sorting algorithms, n log n is the best you can do, to my understanding.
Yeah.
That's the reason. Okay.
Yeah.
Oh,
yeah.
okay.
In general, for comparison-based sorting, there's some sorting algorithms which are n, but in the general case, they don't work. So I guess here, again, I'm not sure. So Pranav asked me about this. So, and I told him, I explained him why big O of n is the answer, because that's what I get as the correct one in the quiz. But if Professor Lee said it's not, maybe he meant for comparison-based sorting.
Okay, so it is wrong, but for the different reasons than I thought. Okay.
Yeah.
Let me tell him that we'll need to fix that one.
Yeah. So I'm not sure. It's just not clear in the question. Like both could be the correct answer. He just needs to specify which type of sorting algorithm.
Wait, so if the answer gets like changed, how does that affect us if we already finished the thing? Is like, are we still fine with whatever grade we got?
I don't know. We're not in charge of the quizzes. I guess if a question is
Yeah.
found to be wrong, everyone gets a point on that question.
Okay.
I didn't attend lecture. Did he mention all of n's time sorting algorithms?
He was talking about like the complexity and like that kind of stuff, but I don't know if he went into the sorting. Or he did go into the sorting, I guess, but yeah.
Oh, actually, I should have done this earlier, but do you mind if I stop the recording? I'm probably not going to discuss too much after this point. I think we'll just do that then.